Hello and welcome to Physics 1A. In the first half of this course, you're going to be learning about mechanics. Now, I'm Associate Professor Elizabeth Angstman. Everybody just calls me Liz. I'm your lecturer for the first half of the course on mechanics, and I'm also the first year physics director. So if you've got any questions about the physics in this course or the administration of the course, then you can come and see me. My office is in the old main building, which is the same building as this lecture theatre is in. My office number is G61F. So the G stands for the ground floor, and then my office number is 61F. I do have an external door onto the corridor, so you can just knock on my door. It's got my name on it, and if I'm available, I'll open the door for you. So my consulting hour is from 12 to 1 p.m. on Wednesday, so feel free to come and see me at this time if you've got a longish question. If you've got a shorter question, I will make sure that I hang around after the lectures. We'll just need to step outside the lecture theatre and I can answer your questions. Now, my email address is here. It's also all over Moodle, so if you need to contact me, that's probably the easiest way. Okay, so let's just have a brief discussion of the administration matters for this course. Now, basically, to understand how this course runs, you're going to need to be familiar with the Moodle site. So let's have a look at the Moodle site now. Okay, so when you log into Physics 1A, it should look something like this. Up the top, you're going to have the next 3 weeks, and this will be a helpful summary for you about what's due each week. Each week I'll also post up an announcement which will be emailed out to you as long as everything's set up in your forums properly about what's coming up in the following week. So in order to see everything, we'll just need to open all the toggles. So you've got your course information, you've got your syllabus, course outline, course pack. So from your course pack, you can download and print the laboratory manual and homework booklet if you want to. Alternatively, you can buy the lab manual from the bookshop. You've also got past exams, which will be useful for studying once you get a bit further on in the course. Now you've got your lecture notes. You're able to download the lecture notes from under the mechanics heading. If you miss lectures, you may want to use these web stream lectures in order to catch up. Below that, you've got your laboratory section. So before each lab, there's a pre-work test that you'll need to do to help you prepare for the lab. There's also a safety induction that you should complete in the first week. So below that, we've got the problem solving workshop. So these are the things known as other in your timetable. So in week 1, you'll be learning about uncertainties in the problem solving workshop. You can access the resources that will be used in class here. Now, each week, you're going to have a quiz due. So each of these quizzes has 4 questions, which are based on the 4 lectures from the previous week. So the first of these will be available at the end of week 1, and it'll cover the content which you've learned in week 1. In order to get ready for it, it's a good idea to do this stack orientation exercise. This will teach you how to input answers into these quizzes. Twice during the term, you're then going to have quizzes which are pulled from the same bank of questions available to you, and these will be held in the first year lab, but you'll find out more about those later. With the at-home quizzes, you can do them as many times as you want and your highest mark counts. Now you've also got access to homework sets. You have videoed solutions to each of these. These will be put up progressively throughout the term. It's a good idea to practice answering the questions yourself before watching the solutions, which is why they're not all just available at the start, but they will all become available during the term. And then we've got discussion forums. So if you have any questions about the course, you can ask them here. Administration forum, so that's just questions about anything. Mechanics, so that's if you've got questions about mechanics. Quizzes, that's if you've got questions about these quizzes here. And lab, obviously if you've got a question about lab or problem solving workshops. Okay, so that's the Moodle site. Now, one of the things that students often struggle with in this course is setting aside enough time for it. Now, the rule of thumb for university courses is that a 6 unit of credit course should take you 150 hours over the term, and that's consistent with this course as well. So deciding how to spend your time, my recommendation would be spend 4 hours each week in lectures or if you've enrolled in the web stream, then working through those lectures online. You should spend 2 hours a week each week attending problem solving workshops and 2 hours a week each week in the lab. So that's 8 contact hours each week. Now, in addition to this, you're going to need to set aside about 1 hour to prepare for the lab, about 2 hours to work through the weekly online quiz, and then around about 3 hours to complete problems from lectures and the homework booklet. So this is all put in your course outline, and you'll receive a printed copy of that in your first problem solving workshop. But if you follow these guidelines, then you'll have around about 20 hours at the end of the term left for preparing for your final exam. Now, the textbook reference for this lecture, so each lecture I'll give you the reference to the textbook in case you want to read up on anything or find some extra practice problems. So this lecture will be looking at vector notation, adding vectors, units, significant figures, and graphing motion. So it's covered in the textbook, Halliday, Resnick, and Walker, sections 3.1 and 3.2, as well as chapter 1 and chapter 2. So a fair amount of content this lecture. So much of this will also be covered in Mathematics 1A. So for example, vector notation you'll find comes up in mathematics as well as in physics. Okay, so some of this will be familiar to you if you have studied HSC physics or if you have already completed the Maths 1A course. Some of you will be studying Maths 1A at the same time. So we have 2 different types of quantities. We've got vectors and we've got scalars. Vectors are things that have a magnitude and a direction. Scalars are things which just have a magnitude. So we can identify each of the following quantities as either a vector or a scalar. Now, temperature is a scalar. We can't have a direction to a temperature. Temperatures can be increasing or decreasing, but the temperature itself, like 22 degrees C, doesn't have a direction, so it's a scalar. Mass is the same. We don't have 1 kilogram north or 1 kilogram with any direction. We just have the mass 1 kilogram. Velocity is a vector. So when we're talking about the velocity of something, we need to give a direction with it. So we could give a velocity of 5 meters per second north, for example. Time is another scalar. This one doesn't have a direction, just a magnitude. Distance is actually a scalar as well. So when we give the distance between 2 points, we give it as 5 meters. We don't give it as 5 meters north. If we were giving it as 5 meters north, it would instead be a displacement. So distance and displacement are very similar to each other, as we'll see very soon. But displacement is a vector having a direction, while distance is just a scalar, so it's only got the magnitude. Now, you'll learn to write vectors in unit vector notation in Maths 1A. So some of you have probably already seen this, but for others it's new. So unit vectors are vectors which have magnitude 1. That's why they're called unit. So a unit vector in the x direction is written with the letter I, and we put this little symbol over the top. The symbol is called a hat. So this represents a vector with a magnitude of 1 in the I, which is the x direction. Now j is a unit vector in the y direction, and k is a unit vector in the z direction. So if we want to write a vector in unit vector notation, such as this one, let's have a look at how we can go about it. So with this vector along the x-axis, we've got this length here. So if we drop this line down here, now hopefully from trigonometry you remember that if we want to work out this length here, we'd work it out as 10, which is this length here, times cos 30. So 10 cos 30 is equal to 10 times root 3 on 2, which we can write as equal to 5 root 3, or we can evaluate it and write it as 8.7 meters. So that gives us the length of this side here. And so we've got 8.7 I. So because I'm writing this by hand and I can't write bold, I've put a little squiggle underneath my I to show that it's a vector. And then the y direction, the j direction, is up here. So this is going to be given by 10 sine 30. Sine of 30 is a half. So this will be 10 on 2, which will be 5. So we'll have plus 5j. So that's how we write this vector here in unit vector notation. Now, a hint, usually it's much easier to solve problems in unit vector notation than to try using the vectors in this format here with a magnitude and an angle. Okay, now we've briefly discussed bits of this before. So we discussed that scalars have a magnitude but no direction. So examples of scalars are distance and speed. So speed is equal to the distance over the time, but again, we'll be looking at that in more detail very soon. Vectors, the equivalent vectors are, for distance, we've got displacement. For speed, we've got a velocity, which is a displacement divided by the time. And then for acceleration, we've got change in velocity divided by change in time. So we'll be looking at acceleration more next lecture. So now if we want to show something is a vector, we can write it in boldface, which works if we're typing, or we can draw a squiggly line underneath it, which is usually what I do when I'm writing on the board. Or we can put an arrow on top of it. So all of these are ways of showing that the quantity that we're talking about is a vector, so it has a magnitude and a direction. So let's consider distance and displacement, which are similar but slightly different. So distance gives the total path length and along which an object has traveled. So for example, if I was to consider a particle which went loop-de-loop and back to its starting point here, then the distance it's traveled is the length of this line here. Displacement, on the other hand, is given by the change in position. Now, there's quite a lot going on in this equation. In physics, we often use delta, which this is the Greek letter delta, the capital delta, to represent a change in something. So this is saying the change in x or the change in position. So the displacement is given by the change in position, which is xf, where this f stands for final, minus xi, where this I stands for initial. So you'll come across the change in something as equal to the final something minus the initial something an awful lot as we go on in physics. So if we were to calculate this displacement here, well, the final position is here and the initial position is here. So these two are the same, and so the displacement in this case is 0. So let's do a couple of examples. A particle travels around a circle. Okay, so let's draw a little diagram. It's always useful in physics to draw a diagram. So it's traveling around a circle. The circle has a radius r. If it travels once around the circle, okay, so it can start here, it goes once around and comes back. What distance has it traveled? Well, the distance it's traveled is the circumference of the circle. So that's given by 2 pi r, the circumference. And what is its displacement? Well, we know that the displacement is equal to the final position minus the initial position, and these are the same. So this is equal to 0. So the displacement is 0. Example 2. So a boy walks 10 meters north. So let's have our boy starting here. So this is x initial. He then walks 10 meters north. So here he is. This distance here is 10 meters. and then he walks 5 meters south. So now he's walking down here 5 meters, and this is where he ends up. So this is x final, the final position. And we're asked, what is his displacement? Well, his displacement is equal to the final position minus the initial position. So if we call this place the origin, then the final position, looking at this, if it's 10 up and then 5 down, this distance here must be 5 meters. So this is equal to 5 meters minus the initial position, which is 0 meters. So this is equal to 5 meters. So his displacement is 5 meters. The distance he's traveled, well, he walked the 10 meters up and then he walked the 5 meters back. So this is 10 meters plus 5 meters, and so this is equal to 15 meters. Now, because displacement is a vector, I should have given a direction with my 5 meters. So I should have said this was 5 meters north. Back on the last example where it was 0, if something 0, 0 doesn't have a direction, so we didn't need to worry about it in that example. Okay, so what you might have seen us doing there was adding two vectors. So we're going to have a look now at a couple of different methods that we can use to add and subtract vectors. So method 1 is the head to tail method. So with that, we need to know how to represent vectors to start with. So it's useful to represent vectors as an arrow. The arrow head shows the direction that the vector is heading. And then we call the arrow head the head, and the other end of the vector is called the tail, which is why we're adding them head to tail. So let's see how we can do that. Let's say that we want to add this first vector here, which is 10, and that's 45 degrees above the horizontal, to 10 this way. In order to do that, we add them head to tail. So here's the head of the first vector, and here's the tail of the second vector. We join the tail of the second vector to the head of the first vector like that. So that has been done for us here. And now what we need to do is evaluate this resultant vector here. So you probably remember from school how we can do that. We can use trigonometry. In this case, we can work out what this angle in here is. That angle in there is 90 degrees. If this angle here is 45 degrees, then this angle here must be 45 degrees as well. Alternate angles on parallel lines. So that tells us that this angle in here is 45 degrees. So the total angle around here, we've got the 45 plus the 90. So this is 135 degrees. And so using our cosine rule, we've got a squared is equal to b squared plus c squared minus 2bc cos a. And so this is our angle A, and this is side A. And we've got sides B and C. And so we can say, well, this is 10 squared plus 10 squared minus 2 times 10 times 10 times cos 135, which gives us our a squared is equal to 341, which gives us our a is equal to 18.5 meters. Now, this is a vector, so we also need to give a direction. So it'd be nice to find out, well, what's this angle here? Let's call this angle here theta and try and work out what it is. Well, what we can do is we can work out what this angle in here is. Let's call that one phi, and we can use our sine rule. So we can say, well, sine phi over the opposite, which is 10, is equal to this one. This is our angle A, which is 135, over A, which we've now worked out. And so this gives us, rearranging, we've got phi, because we take the inverse sine of 10 times sine 135 divided by 18.5, and we end up with phi is equal to 22 22.5 degrees. So if that's 22.5 and this whole thing here is 45, that tells us that this thing is 45 minus 22.5, which is also 22.5. So we've got A is equal to 18.5 meters, and this is 22.5 degrees above the horizontal. Sorry, the pencil's not picking up especially well right now. Okay, so that's one way that we can add these two vectors together, by adding them head to tail. And you'll notice I represented the resultant, which was going from the tail of the first vector to the head of the second vector, with a double arrowhead like this, which is a notation that we commonly use to show that something is the resultant vector. Now, if we want to subtract vectors, so if instead of adding these two vectors, we wanted to subtract them, what we need to do is add them, but flip the vector which is being subtracted. So this is equivalent to that plus this vector here. So then what we do is we take the head of the first vector and we add the tail of the second vector to it. So we're going to have something like this, which is what's drawn down here. So then once again, we can go back to that long method using lots of trigonometry to work out what this is. So if we call this side A and this angle A in here, we can work out what angle A is, because this line is parallel to this line. This is a horizontal line, another horizontal line. So if that's 45 degrees, then alternate angles on parallel lines, this is 45 degrees. And so we have A squared is equal to B squared plus C squared minus 2BC cos A. Substituting in 10 squared plus 10 squared minus 2 times 10 times 10 times cos 45. And solving this, we end up with A squared is equal to 58.58. And so this gives us A is equal to 7.65. But then once again, it's a vector. So we need to work out the angle. So what we'd like, one way to do it is to find out what's this angle in here. So that part there is 45 degrees, because these two sum together to give 90. So what we can do is say, well, sine of theta plus 45 over 10 is equal to, we know A now, so this is sine of 45 over 7.65. And so solving this, we end up with theta plus 45 degrees is equal to 67.5 degrees. Sorry, I'm not sure why it's not writing very neatly. And so theta is equal to 22.5 degrees. And so this is 7.65, 22.5 degrees left of vertical. Okay, so doing it that way took a bit of time, but there is a faster way to do it. We can also add and subtract vectors by breaking them into their individual components. So let's do that now. Now we've got, this is the same original vector here at 45 degrees, but we've now split it into a horizontal component, which we can calculate as 10 cos 45, and a vertical component, which we can calculate as 10 sine 45. So just using our rules from trig, we know that this is equal to 10 on root 2, and this is also equal to 10 on root 2. So this one here is in the vertical direction, so this is J, and this one here is in the horizontal direction, so I, and this vector, this is in the horizontal direction, so this is I. So when we're adding vectors component-wise, we add all the vectors in the same direction. So we've got I times 10 on root 2, plus we've got 10, and then we've got this one here. So this is 10 on root 2, j. So that is one way that we can write this total vector. We can also use a calculator to evaluate it, and if we do that, we can write it as 17.1i plus 7.1j. Now it asks us, does it agree with the result you obtained adding them head to tail? Okay, so if we want to work out what this will be when we add these head to tail, then we've got 17.1 this way and 7.1 this way. So adding these like this, we just use Pythagoras' theorem because these are at right angles with each other, so we don't have to worry about that cosine rule. So this is the square root of 17.1 squared plus 7.1 squared, and evaluating that, we end up with 18.5, which is the same as what we got as the magnitude of the vector when we added them that first way, head to tail. Now we should also check the angle, so let's calculate this theta. Now we know the opposite and we know the adjacent, so we can use tan theta. So tan theta is equal to 7.1 over 17.1, and solving this gives us theta is equal to 22.5 degrees. So we've got 18.5 and an angle of 22.5 degrees above the horizontal, which is exactly the same as we got last time. So we're asked here which method is easier. Well, at least for me, I found this method, breaking them into components and then summing them, took a lot less time. So if given the choice, I would use that method. Now, if you want some practice, in homework set 1 for Phys 1121, there's questions 3 and 4, and for 1131, there's questions 4 and 5. Okay, so we've seen how to add vectors now, and we've seen what displacement and distance are. So now what we're going to look at is how to calculate the average velocity and speed. So the average velocity is given by the equation, which is change in x, which is our displacement, divided by the change in time. So this is the final position minus the initial position divided by the final time minus the initial time. Now we can also calculate an average speed. The average speed is given by the total distance traveled. So distance, that was the total path length over which our object went, divided by the change in time. So question, do average velocity and speed have to have the same magnitude? So the answer to this is no. If we think about that particle which was going around a circle, then the total displacement, once it had gone around the circle once, was 0. And so the average velocity would be 0. But the average speed was the circumference of the circle divided by however long it took to go around the circle, which wasn't 0. So they don't have to have the same magnitude. Now, we can also calculate the instantaneous velocity and speed. So this tells us how fast something is traveling at that instant. So to do this, the instantaneous velocity is given by the limit as our time interval becomes really, really small. And it's the change in the displacement over that time interval divided by the time. So this is dx dt. And the speed is just the magnitude of this instantaneous velocity. So this is the instantaneous speed. So in this case, obviously they do have the same magnitude. It's just that the instantaneous velocity also has a direction as it is a vector. Okay, so let's have a look at an example. So in this example, we've got a particle moves along the x-axis. Its position is described by the equation x is equal to 5 plus 2t minus t squared, and we're going to work out the displacement of the particle in the first 5 seconds, the distance that it travels in the first 5 seconds, the average velocity, and then the instantaneous velocity of the particle at a couple of times. So let's just pull up a separate page to do the working for this on. Okay, so in this question we had x is equal to 5 plus 2t minus t squared. And in the first part, we're asked what is the displacement of the particle in the first 5 seconds. So we know that the displacement is equal to the final position minus the initial position. And so the final position, that's x when t is equal to 5. So that'll be 5 plus 2 times 5 minus 5 squared. And then we need to subtract off the position at the initial time, which is t equals 0. So this will be 5 plus 2 times 0 minus 0 squared. So this will be 5 plus 2 times 5, so that's 5 plus 10, 15 minus 5 squared, which is 25. So this will be 15 minus 25, and then this term's 0, this term's 0, so we've got minus 5, and so this is equal to minus 15 meters. And this is along the x-axis. That's what this x shows. And then part 2 is actually a bit harder because this asks us for the distance. So what we need to work out is exactly how is this particle moving. So really what we'd like to do is plot a little diagram showing if this is time here, what's x. So at time 0, we calculated it here for this part, its initial position, it was at 5 meters. But what it's tracing out here is a parabolic path. So there's a few different ways that we can sketch this parabola. One way to do it is to realize that the because it's got a negative in front of the t squared term, it's going to be an upside down parabola like this one. And what we want to do is work out, well, where's that maximum peak going to be, which we could differentiate to find, or if you remember your equations for the vertex of a parabola is given by minus b over 2a, where b is the thing in front of the unsquared term, the linear term. So this is equal to minus 2 over 2 times a, in this case, is minus 1. So this is equal to 1. So we've got at 1 second, it's reflected about this. So then if we substitute in our 1 second, we have x at 1 second is 5 plus 2 minus 1, and so this is equal to 6 meters. So it gets up to 6 meters at 1 second, and then it starts coming back down like this, and we need to evaluate it at the final position, which we've done here, and this was 15 minus 25, so that was minus 10 meters. So here we've got minus 10 meters, and this is 5 seconds. So in the first second, it travels from 5 meters to 6 meters, so that's 1 meter. And then it travels from 6 meters down to 0, and then down to minus 10 meters. So here it's going a further 6 meters, and then here it's going a further 10 meters. So the total distance that it's traveled is equal to total distance is equal to 17 meters. Okay, part 3 of this question then asks, what is the average velocity of the particle in the first 5 seconds? So average velocity is equal to delta x over delta t, and we calculated delta x in this first part. So that's minus 15 over delta t, it was 5 seconds. So this is minus 3 meters per second. And this is along the x-axis, so in the negative x direction, back that way. And then part 4 asks us, what is the instantaneous velocity of the particle at t equals 0 and t equals 5? Okay, so the instantaneous velocity v is equal to dx dt. So we're going to have to differentiate our expression for x here. So when we do that, when we differentiate 5, we get 0. When we differentiate 2t, we get 2. And then when we differentiate minus t squared, we get minus 2t. So v at 0 is equal to 2 minus 2 times 0, which is equal to 2 meters per second, and that's positive, so in the positive x direction. And v at 5 seconds is equal to 2 minus 2 times 5, which is equal to minus 8 meters per second. So it's now going in the negative x direction, so back. Okay, now as we go on in physics, SI units are going to be really important. So SI units are System International, so they're an internationally agreed system of units that everybody uses so that everybody can understand everybody else's results. So there are 7 SI units, and every other unit can be made up from a combination of these units. So some of them you're probably familiar with, like kilogram is the SI unit for mass, meters for distance, s seconds for time, amperes for current, kelvins for temperature. You'll be learning about that in the thermal physics topic. Moles tell you about the amount of matter contained within something, and then candelabras, which you won't see in this course, is related to the luminosity of something. So we'll sometimes need to convert from one set of units to another. So the common units that we'll be using at the start is, well, distance is measured in meters, and velocity, we saw that velocity was equal to dx dt, so that's meters divided by the units for time, so meters per second. And next lecture we'll be seeing acceleration, which is meters per second per second. But how do we nicely convert something like 60 kilometers per hour into meters per second? Okay, so if we want to convert something like 60 kilometers per hour into meters per second, we can write 60 kilometers per hour. And now we want to get it into meters. So if we multiply this by, we've got 1,000 meters in a kilometer. You can see we've got a kilometer in the numerator and 1 in the denominator. So those are actually going to cancel each other out, which will be nice. Now we will also want to get rid of this hours. And so if we say, well, there's 60 times 60 seconds in an hour, then we'll be cancelling out this hour in the numerator, in the numerator with the 1 in the denominator. And our units which are left over is we'll have meters per second. So we can solve this on the calculator, and we end up with 16.7 meters per second. Now, the other thing that you'll come across a lot in physics is prefixes. Sometimes we want to talk about really big numbers, and sometimes we want to talk about really small numbers. So with these really big ones, you've probably come across them in computing. So we've got tera, so that's 10 to the 12. Giga is 10 to the 9. Mega, 10 to the 6. Kilo is 10 to the 3, so kilometers, for example. Now, getting smaller, we've got centi, so centimeters, 10 to the minus 2. Milli, which is 10 to the minus 3. Micro is 10 to the minus 6. Nano is 10 to the minus 9, all the way down to pico, which is 10 to the minus 12. And it's not here, but there's femto, which is 10 to the minus 15. So sometimes we need to convert between these. So one example is we could be asked how many centimeters in a kilometer. Well, a kilometer is 1,000 meters, and a centimeter is 0.01 meters. And so dividing 1,000 by 0.01 will give us the answer to this, which gives us 100,000 centimeters in a kilometer. Now, significant figures are something that you're going to need to use a lot as well. So how many significant figures does each of these numbers have? Well, 55, we've got 2 significant figures there. We've got the 5 and the 5 both being significant, so this is 2. Okay, 30. Now, this 1 can actually have one significant figure because this 0 may or may not be significant. So 30 is actually special. It can have 1 or it can have 2, because if it's just written as 30, we don't know if this 0 is significant or not. So this is 1 or 2 significant figures. 121, we've got 3 significant figures there, 1, 2, 3. 500, this is like the 30. We don't know if this 0 is significant. We don't know if this 0 is significant. So this one here is 1 or 2 or 3. And 22.3, we've got the 1 decimal place here, which is significant, and then 2 on this side. So this one here has 3 significant figures. Now, it's important whenever you're asked to give an answer, you should give your answer with the same number of significant figures as the piece of data used in the calculation with the least number of significant figures. So I have not been doing that in this lecture so far. So we'll start to worry about this now. So how many significant figures do you answer this question to? So a car travels northwards at 62 kilometers per hour. That's 2 significant figures. For 51 minutes. That's 2 sig fig as well. And then in an easterly direction at 55.5, that's 3 sig fig kilometers per hour for 15 minutes. That's 2 sig fig. What is its displacement in meters per second? Okay, so we first asked how many significant figures do you answer this question to. So the number of significant figures is 2, 2, 3, and 2. So we choose the smallest of those, which is 2. So we answer this to 2 sig fig. And then it tells us to now answer this question. Okay, so let's start by working out how far it's gone northwards. So the distance that it's traveled is going to be equal to the velocity times the time. So this is just rearranging our equation that the velocity is equal to the displacement over the time. And so this is going to be 62 kilometers per hour. So that's 62 kilometers per hour, and then we times it by 1,000 and divide it by 60 times 60 to get it into meters per second. So this is in meters per second, and the time it travels for is 51 meters. So we also need this in seconds. So we're putting everything into SI units so that we don't make a mistake. So 51 times 60, that's in seconds. So we can see meters per second times seconds. That's going to give us an answer in meters. And so this is going to be 52,700 meters north. And then delta x2, it then goes in an easterly direction. And so that is at 55.5 times 1,000 over 60 times 60 times the time, which is the 15 times 60. And solving that, we get 13,875 meters. And in this case, this is going in an easterly direction, east. So that has not answered it to 2 significant figures yet. So it doesn't tell us if we have to answer it in unit vector notation or with a magnitude and direction. So if we wanted to do it in unit vector notation, we would write our answer as 53,000. Sorry, the pen isn't working very well. Plus 13,000, sorry, that'll be 14,000 because it's to 2 significant figures. J, and then we do need our units, so meters. So that's one way we can do it. The other way we can do it is to draw them head to tail. And so we've got going up, and this is the 52,700. And then we've got going east, which is the 13,875. And this is our resultant here. So to work out this, we just use Pythagoras. So that's the square root of 13,875 squared plus the 52,700 squared, which, sorry, you can barely read. And then solving this on the calculator, we get 54,000 meters. Now I've just given that to two significant figures. I haven't included the extra figures here. And then we need to work out this angle theta. And so to work out that angle theta, we can just use tan theta is equal to 13,875 divided by 52,700. So solving that, we get theta is 15 degrees. So we can say north 15 degrees east is the final answer to two significant figures. So let's start with our first displacement versus time graph. Now in class we had a look at what it would look like if we modeled this out. So if you look at the mouse pointer now, I'll try and do this for you. So basically for the first second it stays still, and then we travel with a constant velocity in the positive x direction for the next 3 seconds, and then for the next second we go backwards very quickly, and then we start going forward slowly at a constant speed again. So that's what this graph here is telling us. It's telling us about what the distance of the object is along the x-axis with the time. So we can actually calculate the velocity from a distance versus time graph. So the velocity, it turns out, is given by the gradient. So we can calculate the instantaneous velocity at 1 second. Okay, so we want to work out what's the instantaneous velocity at this time, which means exactly how fast is the object traveling at this time. So instantaneous velocity is equal to dx dt. And so that's the gradient of this line. So for 1 second, which is here, we want to calculate the gradient here. So the gradient is just given by the rise, which is going from 0 to 3, divided by the run, and again it's going from 0 to 3. So the gradient is equal to 3 over 3, so that's equal to 1. So here we've got the velocity is equal to 1 meters per second. That's the instantaneous velocity, and it's along the positive x-axis. Then we need to calculate it at 6 seconds. So 6 seconds is here. And here the displacement is not changing, so the rise is actually 0 divided by the run. We've still got 0, so it's not moving at this point. So the velocity here is equal to 0 meters per second, and then at 8 seconds, so 8 seconds is here. So now we're trying to work out what's the velocity here. So we need to know the gradient for this part. So the gradient for this part is equal to rise over run. Now we're going from 3 up to 10. So the rise is 10 minus 3, and the run we're going from 7 seconds to 10 seconds. So this is 10 minus 7, and so this is equal to 7 over 3 meters per second, which you could work out on a calculator if you wanted. If we do that, we get that this is equal to 2.33 meters per second. And again, this is along the positive x-axis. And now we're asked to calculate the average velocity over the 10-second period. So the average velocity is equal to the change in displacement over the total time. And we are going from 0 meters up to 10 meters. So that's 10. And then the time is over a 10-second time interval, so it's 10. So this is equal to 1 meters per second, and this is along the positive x-axis. Sorry, blocky writing again. Okay, so next we can look at how to calculate acceleration. So acceleration is the rate of change of velocity. So just like with velocity where we had average and instantaneous velocities, we have the same with accelerations. So the average acceleration is equal to the change in the velocity over the entire, divided by the total time period. The instantaneous acceleration, however, is the limit as the time period gets really small, which is just the derivative of the velocity. So this gives us the instantaneous acceleration. So let's continue a bit with this question that we did in the last lecture. We calculated the instantaneous velocity at t equals 0 and at t equals 5. We're considering a particle moving along the x-axis, and we've got its position described here. And remember, it was moving like along a parabola. So this one was following a parabolic path where it was starting at 5 meters. Distance was increasing and then decreasing a bit like this. And we're asked, what is the average acceleration of the particle over the first 5 seconds? So we want our average acceleration, which is equal to delta v over delta t. This is equal to the final velocity minus the initial velocity over the time interval. And we calculated these. So we've got that our final velocity was equal to minus 8 meters per second. Our initial velocity was 2 meters per second. And our time interval was 5 seconds. So this is equal to minus 10 divided by 5. So this is equal to minus 2 meters per second. And then acceleration is a vector as well. So this is the negative, shows that it's going in the negative x direction. So i.e. in negative x direction. Now it says, what is the instantaneous acceleration of the particle at t equals 0 and t equals 5 seconds? So for that, we're going to need to differentiate. So we can get our expression for v because it's dx dt. We did this last time, but I don't have it written here. So we're just differentiating this again. So this is 2 minus 2t. And so a is equal to dv dt, which is the second derivative of this. So when we differentiate this again, we end up with minus 2. And so that tells us that the instantaneous acceleration at 0 and at 5 seconds is minus 2 meters per second. So a at 0 is equal to minus 2 meters per second, and a at 5 seconds is equal to minus 2 meters per second. And so again, this negative shows that it's going in the negative x direction. Okay, so now we're looking at a velocity, that's the velocity on the y-axis, versus time on the x-axis graph. And we're asked which of the following quantities can be obtained from the graph. Part 1, the initial position. Well, the graph doesn't actually tell us anything about where the particle starts from. So we can't actually read this one off the graph, so that's a no. Okay, now the next one is the initial speed. Now remember that speed is the magnitude of the velocity, and this is a velocity time graph. So we can read the initial speed of the graph. Initially, here, it's going at 0 meters per second. So the initial speed is equal to 0. It asks us, can we calculate the initial acceleration? Well, acceleration is related to velocity through dv dt. So acceleration is the gradient of the velocity time graph. We can read off this initial gradient. This is a flat line, so it's a gradient of 0. So the initial acceleration is also 0. Now, can we calculate the total distance traveled? We can, in fact, calculate the total distance traveled. The distance traveled is equal to the area under the graph, because the displacement is equal to the integral of the velocity with time. Now, this is asking for distance rather than displacement. So when we're considering displacement, we take the areas on top of the graph as positive and the areas underneath as negative. However, when we're working out the distance, we will want to add these two areas together. So let's work out what these areas are. We can either treat this as a trapezium, or we can treat it as a series of triangles and a rectangle. Let's just do the triangles and the rectangles this time. Okay, so this triangle here, we've got a length of 1 and a height of 1, so it's got an area of a half. This rectangle here, length of 2, height of 1, so this has got an area 2. And then we've got this triangle, which has got a length of 2 and a height of 1. So half the breadth times the height gives us 1 in this case. So the area on top is 3.5 meters. So it travels 3.5 meters in the positive direction, and now it's going in the negative direction. So now we work out the area of this triangle here, and we've got a length of 2 and a height of 1. So this one here also has area 1, but it's in the negative direction. So the total distance traveled, we add these together and we get 4.5 meters. To get the total displacement, we're going 3.5 meters in the positive direction and then 1 meter in the negative direction. So we subtract those and we get 2.5 meters in positive direction. And then we're asked, can we calculate the average acceleration? We can calculate the average acceleration because the average acceleration is equal to the final speed minus the initial speed over the time. So the final speed, we can just read that off this graph here. The final speed is velocity. The initial velocity is 0. And then we divide by the total time. We're going from 0 seconds to 8 seconds, so 8. So this is equal to minus 1 over 8 meters per second per second. Now the next thing we're asked to do is for this same graph that we were just considering to draw a displacement versus time graph and an acceleration versus time graph. So let's work on this. Okay, so between 0 and 1 second, the object is not moving. So the displacement is 0, it remains at 0. Now between 1 and 2 seconds, it's getting faster and it's traveling this area here, which we calculated that area and we saw that it was equal to a half. So let's put some numbers here. Let's go 1, 2, 3, because we calculated in the last question that the maximum displacement was 3.5. So these are reasonable numbers here. So between 1 and 2 seconds, it's going faster and faster to get to half. So this is half a meter. So since it's going faster and faster, we'll draw it as a parabola like this, which is curving upwards. Now between 2 and 4 seconds, the velocity is not changing. So if the velocity is not changing, that tells us that the displacement versus time graph is going to have a constant gradient. And we calculated this area as well and found it was 2. So it will end up at 2.5 meters. So that's half a meter plus the extra 2 meters. So at 4 seconds, we want it to get to here and it gets to there using a straight line. That should be a straight line. Sorry, my drawing skills aren't brilliant. Obviously in an exam you'd use a ruler if you were asked to do something like this. Okay, and then this area here we calculated as 1, so it's now slowing down. So we want to get to 3.5 meters, and we get to 3.5 meters at 6 seconds. So this is where we want to get to, but we've got a parabola turning the other way, so it's going slower here. This is less steep, this is more steep. Okay, now between 6 and 8 seconds, it's going in the negative direction. So this tells us that the displacement is decreasing, but it's happening at an increasing rate. So we're going backwards. We worked out this area was 1 as well. So we want to get back to 2.5. So here. So this shape here is a parabola with its peak at 6. So that's what the displacement versus time graph looks like. Now the acceleration is the gradient of the velocity time graph. So just so that we don't get confused, let's switch to blue for the acceleration. So my working to do with acceleration, I can write on in blue. Okay, now between 0 and 1 seconds, the gradient here is 0. So between 0 and 1, we've got no acceleration. Between 1 and 2, we've got a gradient of rise, which is 1, divided by run, which is 1. So between 1 and 2, the acceleration is 1 meter per second. So we'll go like that. Now between 2 and 4, the gradient up here is again 0. So it's not accelerating at that point. So that's 0. And then between 4 and 8, we've got a constant acceleration. So we can work out what this acceleration is using rise. So we've got a rise of 2 and a run of 4. So the acceleration is equal to 2 over 4, which is equal to 1/2 meters per second. So, but that's minus 1/2. So we've got minus 1/2 here, and that's to there. That should be a nice flat line. So that's what our acceleration versus time and our displacement versus time graphs will look like. Okay, so just to highlight a couple of important points, displacement is the area under a velocity versus time graph. And for complex curves, we might need to find this through integration. Acceleration is the gradient of a velocity versus time graph, and this can be found by differentiating the expression. So here's an example problem. The velocity of an object is given by v of t is equal to 5 minus t. The object starts from the position x equals 2, and in part 1, we're asked to sketch a velocity versus time graph for the object for the first 10 seconds of its motion. Okay, so we're just trying to sketch v of t is equal to 5 minus t. So we'll want to put t along here, and we'll want to put v up here. Now, when t is 0, we've got 5 minus 0, so this starts from 5. And at 10 seconds, we've got 5 minus 10, so it ends at minus 5. Now, you can see that this is just a straight line with a gradient minus 1. So that's because v is equal to 5 minus t. And just remember that our equation for a straight line is y is equal to mx plus b. In this case, we've got v along the y-axis. The gradient is the thing in front of the x, but along the x-axis we've got t. So in front of the x here, we've got minus 1, and then we've got plus 5. So the y-intercept is 5, so we've already noted that when t equals 0, it goes through 5, and the gradient is minus 1. So we can draw this as a straight line. Sorry, that's meant to be a straight line, and it crosses through here. V is equal to 0 when t is equal to 5. So that's at 5 seconds, and this is at 10 seconds, and that's at 0 seconds. So now part 2 asks us to write an expression for the displacement of the object. So the displacement, which we can represent as s or x, is equal to the integral of the velocity with respect to time. So the opposite of differentiating is integrating. So that's what we do to velocity to get the displacement. And so we're integrating 5 minus t dt. And so this is equal to 5t minus t squared on 2. And then there's no limits on our integral, so we'll end up with a plus c. So what we'll want to do is work out what c is. And to work out what c is, we can use this x is equal to 2 meters at the start. So that tells us when t equals 0, x is equal to 2 meters. And so we can put 2 is equal to 5 times 0 minus 0 squared on 2 plus c, which tells us c is equal to 2. So this tells us that x is equal to 5t minus t squared on 2 plus 2. Now we're asked to sketch an acceleration versus time graph for the object. Okay, so we know that acceleration is equal to dv dt, and so we just need to differentiate our 5 minus t, and that's just equal to minus 1. So this is a nice graph to draw. It's a bit boring. Here's the acceleration, here's the time, here's minus 1, and it's just a straight line like that, always at minus 1. So that's from 0 seconds up to 10 seconds. And then part 4, we're asked to describe in words the motion of this object over 10 seconds. Okay, so looking at the velocity time graph, we can see that the velocity is in the positive direction but decreasing, and then it's in the negative direction. So how we can describe this in words is, well, the object starts at 5 meters. It moves in a positive direction, but with a decreasing speed for the next 5 seconds. At 5 seconds, it's at rest and it changes direction. It then speeds up at a steady rate over the next 5 seconds, ending up at a position of -5 meters. Okay, so another example problem with an acceleration versus time graph. So we're told that the particle shown in this graph starts from rest at the origin. The first question is, what is the initial velocity? Well, that's really not too hard because the question tells us that it starts from rest. Now, if it starts from rest, that means that the initial velocity is 0. We're then asked to sketch a velocity versus time graph. So let's do that here. Here's velocity, here's time, and we've got one. Okay, so now we've drawn our axes. Let's sketch this. Between 1 and 3 seconds, the velocity is the area under an acceleration versus time graph. Now, this is a triangle, so the area is half the base times the height. So this is 1.5. And so that tells us that at the end of 3 seconds, the velocity is 1.5 meters per second. And because the acceleration's changing at a constant rate, we've got this gradient here. The velocity versus time graph is going to be a parabola. So that's exactly the same as when we had a velocity time graph and we were drawing the displacement graph. We ended up with a parabola. So here's a parabola. Now between 3 and 5 seconds, it's accelerating at a constant rate. If it's accelerating at a constant rate, that's going to be a straight line on a velocity versus time graph. Now let's calculate how much the velocity changes. How much it changes is equal to the area under the curve here, which is just a rectangle, height 1, width 2, so it's got an area 2. So we are going up to 3.5 meters per second, and we'll do that with a straight line. So this is a straight line. And then between 5 and 6 seconds, the acceleration is decreasing at a constant rate. So we'll have a parabola again. And the change in the velocity is the area under this curve. So this is a triangle with height 1 and width 1. So that's got an area a half. So we're going another half a meter. So we're going up to 4 meters. So at 6, we've got a parabola like this. So this should all join up. And then between 6 and 7 seconds, the acceleration is negative. So it's slowing down. This again has an area a half. So once again, because the acceleration is changing at a steady rate, the velocity versus time graph is a parabola. And it's equal to 0 at 6 seconds. The acceleration is 0. So we've got a tangent which is straight at 4 seconds. Now, between 7 and 10 seconds, we've got a negative acceleration, which is constant. The area under this graph here is 3 times 1, so that's 3. And so we're slowing down by 3 meters per second. So we're going from 3.5 down to 0.5. So this point here is at 0.5, and that's a straight line. So straight, and here we've got a parabola, and this is straight, and this is a parabola. Sorry about my drawing skills. Okay, now part 3 says, what is its displacement at t equals 3 seconds? Now this is a little bit hard because we need to calculate the area under this parabola, which we can't really just use geometry to do. So rather than do it that way, we're going to need to integrate it. So let's start with an expression for the acceleration in the first 3 seconds. So just remembering back to when you were learning geometry in school, you had the equation for a straight line was y is equal to mx plus b. So we can apply that to this part of the graph here. So with this part of the graph, hopefully you can see that the y-intercept, b, is equal to 0. That's that point there. Now the gradient, m, is equal to rise over run. The rise, it goes from 0 to 1, so that's 1, and the run, the time goes from 0 to 3, so that's 3 seconds. So the gradient is 1/3. So we've got ax on the y-axis, so we've got ax is equal to m, which is 1/3, times x, which is t, we've got t on the x-axis, plus b, which is plus 0. So this is our expression for the acceleration. Acceleration is equal to t on 3. Now what we're trying to do is get the displacement. So if we get the velocity is equal to the integral of the acceleration with respect to time. So this is equal to the integral of t over 3 dt. So this is equal to t squared over 6 plus c, but we realized that initially it was at rest. So at t equals 0, we've got v equals 0. So this tells us that c is equal to 0. So we've got v is equal to t squared on 6, and we're trying to get the displacement. So to get the displacement, we need to integrate this again. So x is the integral of t squared on 6 dt, which is equal to t cubed over 18 plus c. And we're also told it starts at the origin. So because it starts at the origin, that tells us that x equals 0 when t equals 0, which tells us that c equals 0. And so x is equal to t cubed over 18. Okay, so now we have an expression for how far it has gone in the first 3 seconds. Now we just need to substitute in our time. So x at 3 seconds is equal to 3 cubed over 18. Now I'm going to write 18 as 3 squared times 2, just because that lets me easily see that we've got 3 over 2, which is 1.5 meters. So it goes 1.5 meters in the first 3 seconds. Now it's just a coincidence that this was 1.5. Those don't necessarily have to be the same thing. So then we're asked in part 4, what is the displacement between t equals 3 and t equals 5 seconds? Now this one's a bit easier because we've got our velocity time graph here, and this is a easier shape to figure out. We've got a trapezium here. So for part 4, we can just calculate the area here. So the displacement is equal to, well, the average height. So it's going from 1.5 up to 3.5. So the average height is 2.5. We could do that 1.5 plus 3.5 divided by 2 if we wanted. And then we times it by the width times 2. So this is equal to 5 meters. So the answer to part 4 is 5 meters. So just highlighting a couple of important points. The velocity is the area under an acceleration versus time graph. So we can find this by integrating if it's a complicated kind of shape, but if it's a really simple shape, it can be easier to use geometry to calculate. So to find the displacement from the acceleration, you actually need to integrate twice with respect to time. That's because velocity is the integral of the acceleration, and then displacement is the integral of the velocity. Then if we're going the other way to get from displacement to acceleration, you actually need to differentiate twice. So differentiating once will give you the velocity, and then again to get the acceleration. So to practice this, if you're in 1131, you can try homework set 1, question 3. Okay, so another example, we're asked to draw an acceleration versus velocity and displacement time graph for a ball dropped from a height of 10 meters. And we're told that we can neglect air resistance. So we'll do that in a second. If you want extra practice, then homework set 1, question 1 is a good place to practice. Okay, so I've drawn axes for an acceleration, velocity, and displacement versus time graph. So for the acceleration, we've said that objects accelerate constantly near the surface of the Earth, and that the rate is given by g. So here we've got g, which is, well, minus 9.8. And this is constant, so it drops like this until it reaches the surface of the Earth. We won't calculate this time exactly now. We're just looking at the shapes of these graphs. Now, if it's being dropped from rest, then we can assume that the speed is initially 0 and it's accelerating downwards, so it's going to have a negative velocity. Because the acceleration is constant, the velocity is going to be changing constantly, which means it's going to have a constant gradient. So the velocity is going to be a straight line going down like this, and the gradient will be equal to minus g, well, minus 9.8. And displacement, it starts from 10 meters because we're told that it's dropped from a height of 10 meters. And now the velocity is changing at a constant rate. So the displacement graph is actually going to be a parabola. So the gradient of the parabola is 0 when the velocity is 0. So this is going to be a parabola like this. So parabola. And then when the displacement's 0, that's when it reaches the surface of the Earth. Now, each lecture we're going to end with a few problems, 2 or 3 problems. We won't necessarily have time to complete these in class, but I will give you the solutions to them. It's a good idea for you to have a go at them, and then if you get stuck, refer to the solutions. Okay, so I've pasted the question up here. It says a jogger runs at a constant speed of 10 kilometers per hour. So the speed is equal to 10 kilometers per hour. They run in a northerly direction for 25 minutes. So 25 minutes north. And then run in a westerly direction for 35 minutes. So then 35 minutes west. Now part 1 says give their displacement in meters in unit vector notation, with I being the easterly direction. Okay, so this is I, and J being the northerly direction. Okay, so we need to get the displacement in meters. So that's an SI unit. So let's convert this constant speed into a constant speed in meters per second. So we've got V is equal to 10 kilometers per hour. Now, if we convert it from kilometers to meters, there's 1,000 meters in 1 kilometer. And then we want to convert from hours to seconds. So there's 60 times 60 seconds in 1 hour. So that'll cancel out our hours and our kilometers, and we'll end up with meters per second. So effectively what we're doing is we're dividing 10 by 3.6. And when we do that, we end up with 2.78 meters per second. Okay, so let's see how far he goes north. He's running north like this, and it's 25 minutes at this speed. So we know that the distance is equal to the velocity times the time. So that's equal to 2.78. This is meters per second. So we actually need the time in seconds as well. It's 25 minutes, so that's times 25 times 60, because there's 60 seconds in a minute. And so this gives us the time in seconds. And so solving that, we end up with 4,166 meters, and this is in a northerly direction. So north is J. So we put a little unit vector after that. So we've got the initial distance, and now he runs for 35 minutes west. So west is in this direction. And so we use distance is equal to velocity times time again. The velocity is still 2.78. The time is now 35 minutes. So that's 35 times 60 to get it into seconds. And solving that, we end up with 5,838 meters. But what we're going to need is a displacement, which is a vector. So this is going in the negative I direction. So we'll put a negative there, and then we'll put an I after it. Okay, so he is basically going north like this, and then west like this, and ending up somewhere over here. But it's quite easy to give this displacement in unit vector notation, because we just add these together. As everything here is given to 2 significant figures, we should give our answer to 2 significant figures. So this is equal to, let's start with the I component, minus 5,800i, and then we've got plus 4,200j. And so that's our displacement in unit vector notation, and it's in meters. We need to include our unit. Okay, so that's part 1. Now in part 2, it asks us what is the average velocity of the jogger. Okay, so the average velocity is equal to the change in the displacement over the change in the time. This is a vector. So this is that vector that we've just calculated here. So this is equal to minus 5,800 plus 4,200 j, this is I, over the time. And this is the total time here. So he's running for 25 minutes, then 35 minutes, and we want this to be in seconds. So we're going to times that by 60. So 25 plus 35, that's actually 60. So we've got 60 times 60 on the bottom. Solving this on the calculator, we end up with minus 1.6i plus 1.2j. And this is in meters per second. So that's how we solved that problem. So our next problem is a particle moves along the x-axis. Its position is described by the equation x is equal to 2t squared minus 7. And then we're going to need to look for its displacement, its distance, average velocity, and some instantaneous velocities. Now, a good way to start this question is with a diagram showing what this equation here means, because we'll need to know if our particle goes forwards, then backwards, or if it just keeps going in the one direction. So let's do a little graph, and we'll put time along the x-axis, and we'll put x along the y-axis. So at time 0, if we substitute 0 into here, you can see it starts at minus 7. So it starts at there. Now at 1 second, we've got 2 times 1 squared minus 7, so that's minus 5. So here it's like here. And then at 2 seconds, we've got 2 times 2 squared, so 2 times 4, so that's 8 minus 7, so it's up to 1 there. And then you can see it's getting bigger now as the square. So at 5 seconds, 2 times 5 squared, that's 2 times 25, so that's 50 minus 7. So what's that? 43. So we end up with a parabola type shape. So let's draw this shape here. It's a bit messy, but it's a parabola. And you can see it's got a minimum here. So if it was going backwards in time, it'd come back up here like this. Okay, so now we can use this to try and solve the problem. Part 1 says, what is the displacement of the particle in its first 5 seconds? Okay, so we want it's only moving in the one dimension, in the x dimension. So the displacement is the final position minus the initial position. So we worked out that it ended up at 43 meters. So this is 43, and we said it started at 7 meters, so minus 7. And so this is 43 plus 7, so this gives us 50 meters. And this is along x. And it's a vector, so we need to give a direction. So we can say along the positive x-axis. And then part 2 says, what distance does the particle travel in the first 5 seconds? So this one isn't too bad because it's not going backwards at all, it's only going forwards. If it only goes forwards, then the displacement and the distance are going to be the same. So the distance is equal to 50 meters. Part 3 then asks, what is the average velocity of the particle in the first 5 seconds? So we want average velocity, and so that'll be the displacement divided by the time. We've got our displacement is 50 meters along the x-axis, and the time is 5 seconds. So this is going to be equal to 10 meters per second along positive x-axis. So again, we've given the direction because of velocity is a vector. And then part 4 asks us what is the instantaneous velocity. So to get instantaneous velocity, we need to use v is equal to dx dt. And so we'll be differentiating 2t squared minus 7 with respect to time, and differentiating this, we end up with 4t. So we want the instantaneous velocity at t equals 0. So when we substitute 0 in here, we get 0, which is what we expect looking at our parabola. If we look at the tangent at t equals 0, which is the tangent down here, you can see it is a completely flat line. So the velocity should be 0. And then the velocity at 5 seconds, which is really related to the gradient of this slope at 5 seconds. We'll learn more about that in the next lecture. And so this is equal to 4 times 5, just substituting into this equation here. And so this is equal to 20 meters per second. And then again, we need to give a direction because it's still a vector. So along positive x-axis. So that's how we solve that problem. So now we're on to the problems at the end of the lecture. So the displacement of an object is described by x is equal to 2t squared minus 3t plus 5. And we're asked to write down an expression for the velocity of the object. So in part 1, we've got x is equal to t squared minus 3t plus 5. And we know that the velocity is equal to dx dt. So we just need to differentiate this. So when we differentiate it, we get 2t minus 3 is the velocity. And then in part 2, we're asked to write down an expression for the acceleration of the object. So the acceleration is the derivative of the velocity, or the second derivative of the displacement. So since we've got the velocity here, we just need to differentiate this. When we differentiate this, we get 2. So this is 2 meters per second per second. And then part 3 asks us to plot graphs showing the displacement versus time, velocity versus time, and acceleration versus time graphs for this object. Okay, so now I've drawn my axes for my displacement, velocity, and acceleration versus time graphs. Okay, so displacement is given by this equation up here. Now we can see that this is a parabola, so it'll be a parabola. We can see that when t equals 0, then we've got x is equal to 0 minus 0 plus 5. So this is going to start from 5. And we can work out where the axis of the parabola are. We could differentiate it and then set the derivative to 0, or we can just use that the axis is minus b over 2a, which is equal to what? 3 over 2. So 1.5. So in this case, because we've got a positive number in front of the t squared, it's a parabola which is going to go like this, curve upwards. Let's work out what the minimum displacement is. That'll be when we put 1.5 into here. So x min is equal to 1.5 squared minus 3 times 1.5 plus 5. And solving that on the calculator, we get 2.75. So here's 2.75. We'll go down there, and then it's a parabola which curves up like this. So getting further and further, faster and faster. Okay, now the velocity, we worked out the equation for the velocity versus time graph here. So at t equals 0, we can see that the velocity is minus 3. And then this is just a straight line graph. We can see that when we can see that it'll go through v equals 0 at t is equal to 1.5, which makes sense because that was where the minimum on our displacement versus time graph was. So this will be 1.5, and then we've just got a nice straight line. So that's as straight as I can draw, trying to go through 1.5. Now the acceleration versus time graph, we've got that our acceleration is constant and it's just equal to 2 meters per second. So we can put 2 there, and this is just a flat line like that. So that solved this problem. Okay, so our next problem. The graph shows the velocity of a car versus time. We're asked, what is the acceleration of the car at t is equal to 30 seconds? Okay, so at 30 seconds, we need to know the acceleration. So we need to know the acceleration here. So in order to do that, we can use that the acceleration is equal to dv dt, which is just equal to the gradient. So we need to work out the gradient of this part of the graph here. So the gradient is equal to the rise. So it's going from 10 up to 30. So we've got the rise is 30 minus 10 over the run. And this is ending at 40 seconds and starting at 20 seconds. So 40 minus 20. So this is equal to 20 over 20, which is equal to 1 meters per second is the acceleration of the cart at this time. Part 2 says, when is the car at rest? Okay, so this part's not too bad. We've got a velocity versus time graph, so it's going to be at rest when the velocity is 0. So we can see that's happening here at this time interval. So it's at rest between 90 and 100 seconds. Part 3 then asks us, how far does the car travel in the 100 seconds shown on the graph? Okay, so for this one, to get how far it's traveled, we need to integrate the velocity, so we need to get the area under the curve. So let's split the curve up into little bits for which it's easy to calculate the area. So between 0 and 20 seconds, we've got a height of 10. So 20 times 10, that's 200, is the distance that it travels. Now between 20 and 40 seconds, this area in here, we have a trapezium. So the area is equal to the average height, which is 10 plus 30 over 2 times the width, which is 20. That's 40 minus 20 to get that 20. And so calculating this, we've got 40 times 10, which is 400. So this area here is 400. Then we've got this rectangle here. This has got a length of 30 and a height of 30. So 30 times 30, that's 900. Now we've got this triangle. It's got a width of 20 and a height of 30. So half the width times the height is 10 times 30, that's 300. And then this one's got 0 area. So to calculate the total distance that it's traveled, we'll just want to add these together. So we've got this is equal to 200 plus 400 plus 900 plus 300, which is equal to 200 plus 400 gives us 600, plus the 900 gives us 1,500, plus the 300 gives us 1,800 meters, or 1.8 kilometers. Part 4 then says, what is the average acceleration of the car over the 100 seconds? So the average acceleration is equal to the final speed minus the initial speed over the total time. These are easy to just read off. So the final speed, finally it's going at 0 meters per second. Initially it's going at 10 meters per second, and this is 100 seconds. So we've got minus 10 divided by 100, which is equal to minus 0.10 meters per second as the average acceleration. Okay, so in this problem, we're told that a ball is dropped from 6 meters. So the initial height is 6 meters in Sydney, where G is equal to 9.80 meters per second. So it's dropping downwards. And we're asked in part 1 to write an expression for the velocity of the ball as a function of time while it falls. So we know that to get the velocity from the acceleration, we need to integrate it. So this is equal to the derivative of the integral of g with respect to t. So this is equal to gt plus some constant. Now at t equals 0, we've got that the acceleration is equal to minus 9.80 meters per second. So now if we assume that it's dropped from rest, we know that v equals 0 at t equals 0. So we've got 0 is equal to g times 0 plus c, which tells us that c must be equal to 0. So v is equal to gt, which is equal to minus 9.80 t. So we've put the negative sign there to show that this is a downwards velocity because the acceleration due to gravity is downwards. Now in part 2, we're asked to write down an expression for the height of the ball. Okay, so we know that the displacement x is the derivative of the velocity with respect to time. So this is equal to the derivative of minus 9.80 t dt, which is equal to minus 4.90 t squared plus c. Now we know that at t equals 0, x is equal to h because it's dropped from height h, which is 6 meters in this case. So we can substitute these in to find out what our constant of integration is here. So we've got 6 is equal to minus 4.90 times 0 squared plus c, which tells us that c is equal to 6. So we can write, well, the height is equal to minus 4.90 t squared plus 6. Now part 3 asks us how long does it take the ball to reach the ground. So to work that out, it'll reach the ground when the height is 0. So here height equals 0. Up here height is 6 meters. So we just want to set 0 is equal to minus 4.90 t squared plus 6 and solve it to get t. So we have 6 is equal to 4.90 t squared. I move this over to this side and divide it by minus 1. And so t is equal to 6 divided by 4.90, and then we need to take that square root. So solving this, I get 1.10 seconds as the time this ball takes to drop to the ground.